All right, so let's talk a bit about count distributions versus sampling distributions, because this is one of the issues that comes up a fair amount. All right. Count distributions versus sampling distributions. So let's say that, so let me do it like this. So let's say I'll refer to count distributions in blue, just to kind of make life easier here. So we'll do count distributions will be in blue. And I will do sampling distributions. I will do that in green. All right. So let's go ahead and start by talking about count distributions. All right. So with a count distribution, the idea is we've talked about binomial distributions. So we have a binomial distribution. And the idea of this is what it does is it allows us to predict the count of how often something shows up in our sample. So how often does a particular value actually show up in our sample? All right. So the key is that these are counts, so they're whole numbers. You can't have part of a thing show up. So either if I have 20 people in my sample, either 18 people have that particular characteristic or 17 people have that characteristic, but I can't have 17.5 people. So consequently, what we have is all of the outcomes in this case, all the random variables, if we want to use the specific term, are between 0 and n, and they're only the whole numbers between and including 0 to n. Okay? This is not the same when we're talking about a sampling distribution. When we're talking about a sampling distribution, we're sampling for proportions of success. In other words, how often do we successfully observe in our sample that characteristic we're looking for, and then we represent that count as a proportion. So in this case, we're not looking at counts, we're actually looking at proportions. Often represented as percentage, which is fine, but the idea is we have our sample proportion, which is given by k divided by n. So over here, really, this value that we're talking about, this count, that count is the value k. And k is in the values 0 to n. Right? Now, where does the p hat exist? Well, the p hat is going to exist between, so the p hat exists somewhere between technically 0 and 1 or 0 and 100%. Now, it is possible that the entire sample is or does not have the characteristic we're looking for. So it is possible to be 0%. In this case, this is an example where it's approximately continuous. It's approximately a continuous distribution as we have larger and larger n's. But technically, it actually is a discrete distribution. In fact, I can even tell you the discrete unit would actually be 1 over n, because that's how the value p can change. Okay? But as a consequence, because it's continuous, a lot of the times we can actually take advantage of the fact that we can actually use the normal approximation here. Okay, and we can use the normal approximation because one, it's continuous, and because when we actually plot the proportions, they actually appear to follow very, very closely follow a normal distribution. All right, so far so good. No, they are not. For it to be binomial, it has to have the 4 criteria. It has to have a fixed number of trials. So n is the fixed number of trials. The proportion of success has to remain constant for every single trial. There has to be only 2 outcomes. And then the results have to be independent. So if we meet those 4 criteria, then our count distribution is indeed a binomial distribution. The binomial distribution is an example of one type of count distribution. So I'm going to clear part of this slide. So let me erase part of this. I'm just going to erase the part down here that we were talking about, the approximation. So I don't really need that. It's interesting to keep in mind, but it's not a big aspect of what we're doing. And we'll remember that we're using the normal approximation, but in truth, we're really going to focus on the normal approximation for all of these. All right, so what we have now is, we can talk about the mean and the standard deviation for our population. So here, the mean of this distribution is given by n times p, the number of trials times the proportion of successes we see in the population. This is the average for this distribution. And in turn, for the counts, the standard deviation has the following formula. It's n times p times 1 minus p, and then we take the square root of that entire product. So I want to stress that this is true. This is true for for counts. So this is true for when we're talking about counts. Okay. When we're talking about proportions, we use the formulas are a little different. And we actually change the notation just a little bit as well. So let's look at the notation we use here. So first of all, when we talk about the mean of the distribution, we actually use a more precise notation. We actually use the notation mu sub p hat to emphasize that we're talking about the average of the proportions. And this is nothing more than p star, the population proportion. The sigma for our distribution, which we indicate is technically a standard error because it's the standard deviation of a sampling distribution. So sigma sub p hat, it looks very similar to what we have over here, but this time n is in the denominator. N is in the denominator, not in the numerator. Okay. So it's p star, the population proportion, times 1 minus p star, all over n, and we take the square root. Now, if I wanted to be technical, I could use the notation p star over here as well, but in this case, we don't really have to worry about, in this case, there is really only one p that we're talking about, and that's the population proportion. So when we're talking about counts, we know that there's some proportion of success in the population, and this is the distribution of these count variables k. Okay. The reason why we distinguish the p's over here with the p star and the p hat, because there's a proportion for our sample, but there's also a proportion or the percentage associated with the population. We need to distinguish those over here. So that's these are the formulas. So be careful of the context. Be very, very careful of the context, because it is going to change which of these formulas you want to use. So there's a difference between the count distribution and the sampling distribution, and you want to pay careful attention to which one you're actually referencing. In the current module, we really are just focusing on sampling distributions. Okay, let me pause if there are any questions on this. No, we generally don't talk about the standard error when we're talking about the counts. We're looking at our sample and saying how many samples would have this particular characteristic. In other words, this particular count. So there's really not a essentially the count is specific to that sample. And in this case, the unit of analysis is the sample itself.
Okay.
Over here, the unit of analysis is still technically each person that makes up our sample. And that's why we're looking for that proportion in the sample. So here we want to know how many individuals are in a sample, and that's the value we're focusing on.
Okay.
The sample, the count in the sample. So the unit of analysis is the sample itself. For sampling distributions, we're still focusing on the individual, and we're asking information about the individual, but we want that information averaged over the sample. That's a really, that's a very challenging question for me to answer, but it's a good, thoughtful question about to sort of tease apart what are the subtle distinctions between these. Yes, but in your mind, you just want to think of the standard error. Standard error is just a fancy title for the standard deviation. It's the standard deviation for a sampling distribution. That's the only reason why we give it that extra title, standard error. But really, it is, for all practical purposes, just a standard deviation.